Hello biology students, and welcome to this video where we're going to be discussing passive transport. And more specifically, within the passive transport category, we're going to be talking about one type of passive transport, which is called diffusion. So first, let's define what we mean when we say passive transport. So we look at the phrase itself, transport, well, we know what that means. It means to move things back and forth. And passive, if you think about English, usually means without energy, right? If you're really passive, you're not moving around, you're not being aggressive, right? So passive transport, if we look at that phrase together, is going to mean the movement of molecules across a membrane without the use of energy, without ATP. So if a cell is doing passive transport, things are crossing the membrane and the cell is not doing any work to do this. It's not burning any ATP, it's energy storing molecule that it made in the mitochondria. It's just happening automatically. So within passive transport, there are many types of passive transport, but we're going to focus in this video on diffusion. And I'm sure you've seen, the concept of diffusion either in life or in previous science classes, but we're going to define it as the tendency for particles to spread out evenly in an available area, right? So if you have a bunch of molecules, they tend to spread out to evenly fill the space they're in. And when they move from an area of high concentration to an area of low concentration. And that's really important. And we're going to spend most of the next couple of slides talking about how molecules move from an area of high concentration to an area of low concentration in diffusion. Now, just in case you aren't aware, concentration we can define as the amount of stuff, the amount of a substance that's in a given space. So in other words, molecules tend to move from where there's a lot of molecules to where there's fewer molecules. And I'm going to show you a picture in a second to kind of give you a visual to think about what that would look like. So here's the picture I was talking about. So let's pretend I had a beaker of water, which I have right here, and I took a dropper and I put a single drop of red dye in the center of that water. Now we know a drop of red dye would contain many, many thousands, if not millions of dye molecules. But when I initially put my drop of red dye into the water, all the molecules of the dye are kind of clumped together, right? In this case, what I've circled there is an area of high concentration of the dye. The molecules are, there's a lot of them per unit area. Now we know from previous science classes that molecules are always in motion if they are above absolute zero, which molecules on the planet are, right? So all of these molecules are moving around, and as you can imagine, as they're moving, they're crashing into one another, bumping into one another, and when they bump into one another, they're going to ricochet off one another, right? And because of this tendency, because when the dye molecules are close together, they're more likely to bump into one another and shoot off in different directions. This means that as the molecules move, they'll tend to spread from being clumped together, like in this first picture, to evenly spread out in this last picture, right? Because the more clumped they are, the more likely as they're moving to hit one another and kind of spread out until they're kind of equally distributed amongst the solution. So we're moving from an area of high concentration, we're moving to where there are a lot of dye molecules, to an area of low concentration, to this area where there are fewer red dye molecules. And when they are evenly spread out like this, we say that those molecules have reached a state of equilibrium. Equilibrium means they are equally distributed throughout the solution. Okay, so at equilibrium, kind of an important thing to note, a misconception that students often have is they think that once molecules reach equilibrium, they stop moving. And that is absolutely false. We know that molecules are always in motion. So at equilibrium, molecules are they have not stopped moving. They have continued to move back and forth. But the key is that there's no net change in concentration of the molecules, okay? So let's talk about this in terms of the example we have here. So in this case, we're actually, in the previous picture, we were looking at just molecules spreading out in a beaker, but here, let's actually look at a passive transport example, molecules moving across a membrane without the use of energy. So in this first example here, this gray line down the center is my cell membrane, and we know that the cell membrane has pores in it from our protein channels. We saw that in the previous video. And if I start with a bunch of one molecule type on one side, all of these molecules are bouncing back and forth, ricocheting off one another, and therefore some of them, just by chance, when they ricochet, will move through the pores of the membrane to the other side. And they're moving from that area of high concentration to the area of low concentration because they're more likely to hit one another on this side. Now, eventually, they reach equilibrium. There are more or less an equal number of molecules on both sides of the membrane. However, sometimes students think that at this point, molecules stop moving. That's not true. What's actually happening here is because the molecules are at an equal concentration, we are equally as likely to get a collision between molecules on this side, sending a molecule that way, as we are to get a collision on this side, sending molecules this way. So what's really happening is we're just getting an equal number of molecules to go right and an equal number of molecules to go left. And when this happens, we say that there's no net change. So a net change means any change going left is canceled out by a change going right. So there is movement, it's just equal movement in both directions. Okay, this would also be true if we looked at an example with two molecules. So here I have a high concentration of green molecules on the left of the membrane, and I have a high concentration of pink molecules on the right. The green molecules are going to move from a high concentration of green to a low concentration of green, which means they're going to tend to move right. And the pink molecules are going to move from a high concentration of pink to a low concentration of pink, so they're going to tend to move left. And then once we've reached equilibrium, we're going to have the same concentration of molecules on both sides. We have approximately equal amounts of green on both sides and pink on both sides. And again, movement hasn't stopped here. It's just that the green molecules are equally likely to cross the membrane in both directions, and the pink molecules are equally likely to cross the membrane in both directions. Okay, so finally, there's one last vocabulary word I would like to introduce, and that's this idea of a concentration gradient. So we've been saying all along that molecules move from an area of high concentration to a low concentration. And another way of saying the exact same thing is that molecules have a net movement down their concentration gradient. So when I say down a concentration gradient, I want you to kind of imagine that like things were going down a hill, right? Like you go from the high part of the hill to the low part of the hill. So if you're going down a hill, you go from high to low. If you're going down a concentration gradient, you're going from an area of high concentration to low concentration. Another phrase you might hear is molecules moving with their concentration gradient. This means the exact same thing, right? Like if you were going with gravity, you would move from an area up the hill to down the hill, right? If you're moving with the concentration gradient, molecules are going to go from an area of high concentration to an area of low concentration. So that's that phrase, concentration gradient, I wanted to introduce here. Now, again, just like molecules move in both directions during equilibrium, molecules also, if I had a membrane here, molecules, the net movement is going down the concentration gradient. You will get the occasional molecule to move up the concentration gradient, go from low to high, but the important thing is that there will be a higher number of molecules going from high to low. And if you have a higher number of molecules going from high to low than low to high, that means we have a net movement from high to low. And passive transport always has a net movement of molecules going from an area of higher concentration to lower concentration. Okay, so molecules do move in both directions because it's a random movement. It just the movement happens from collisions and molecules bouncing off one another. But because you'll get a higher number of collisions where there are more molecules, you will have a net amount of movement from an area of high concentration to low concentration. Okay, folks, that's it for this video, and I will see you in the next one.